All right, problem 7. This is a straightforward Arrhenius plot problem where the rate constant for an elementary reaction has been measured as a function of temperature at a variety of temperatures. We're going to assume that that rate constant obeys Arrhenius behavior. So the rate constant is equal to a pre-exponential factor times e to the minus activation energy over RT. And that, of course, means that the logarithm of K is equal to the logarithm of A minus EA divided by R times 1 over T, which means that a log of K, a plot of the log of K versus 1 over T should give us a straight line, and that's an Arrhenius plot. And so in order to prepare the Arrhenius plot, I first take 1 over T. I just take 1 over all of these values in the first column here. And then I take the natural logarithm of all the values in the second column, and then I just plot the first column versus the second column, or really the other way around, the second column versus the first column. And if that gives us a straight line, like it does here, because this is in fact artificial data, of course, so it's always going to be perfect, but in real life you never know. If it gives us a straight line, then that proves that the reaction obeys the Arrhenius law, at least well enough for our purposes, right? It may not, strictly speaking, obey the Arrhenius law. In fact, there's good reason to believe that no reaction ever truly obeys the Arrhenius law. But if you get a straight line, then for practical purposes, the Arrhenius law is good, and you can continue. The slope of an Arrhenius plot is equal to minus EA over R, and in this case, for this plot, that slope is equal to minus 3586. Notice the units, it's got units of K, and the reason for that is because you're plotting a unitless quantity over here, which is the logarithm of the rate constant, versus something that's got units of 1 over K on the x-axis, and so that's going to give you units of K when you take the ratio of those two, or the ratio of differences between those two to get the slope. Notice also, I didn't point this out, but I should have at the beginning, that the units of K are seconds to the minus 1. That tells us that this is a first order reaction. That doesn't matter for this analysis if it had been second order or 12th order or half order or anything else. We would still do the same things, but it's good to know what the overall order of our reaction is. You can tell what the order of a reaction is by the units on the rate constant always. All right, so now we can get our slope. We got our slope. We just multiply it by minus R, and that gives us an activation energy of about 30 kilojoules per mole. That's a little bit on the low side, but it's well within the very, very normal, very usual range. Now, there are better ways to get the activation energy, but for the purposes of this class, I'm not going to go into that. It's just too complicated at the end of the semester like this. So our way is just to pick one temperature here. So I'm picking this temperature right here. Choose the K value for that temperature. And since K has to, at that temperature, has to be equal to A e to the minus EA over RT, and we now know EA, we can just calculate A as K at the temperature in question over all that exponential stuff. And that's what I've done here, right? A should be independent of temperature. So if you picked a different temperature, if you picked, 320 down here, or if you picked 310 in the middle someplace, you should get the same answer, or very close to the same answer. The fact that if this were real experimental data, there would be noise in this data is why this is not a good method, right? Because then if you choose one temperature, you get a different answer than if you choose a different method. So you got to do some kind of averaging, but let's not bother with that for this semester. All right, so plugging the numbers in, we get a pre-exponential factor of 1.86 times 10 to the 5. Notice the units, seconds to the minus 1. Those units always have to match the units on the rate constant itself, and that is it. Arrhenius plots are a fair amount of work, but they're pretty straightforward.